C. Jerica, and I'm doing this with my colleague Adrian Ponta. Our project is on the heat exchanger simulator. Has it ever crossed your mind how industries cool hot fluids or heat cold ones efficiently? In industries like power plants and oil refineries, heat exchangers are used to transfer heat between fluids, but designing them is complex. Engineers must balance efficiency, cost, and real-world issues like fouling or any other factor that may affect the efficiency of the heat exchanger. Energy efficiency is a major challenge in petrochemical industry, where large amounts of heat are generated and used in processes. The project focuses on one important device that helps to manage this energy, and that device is the heat exchanger. What is a heat exchanger? One may ask. A heat exchanger is a device that transfers heat from a hot fluid to a cold one without mixing them. It is commonly used in industries such as the oil refining, gas processing, and chemical production. Relevant to petroleum or the petrochemical industry, heat exchangers are very important because they help to conserve energy, reduce cost, and maintain proper temperature control. They are used in processes such as distillation, condensation, and cooling of petroleum products. So we developed a Python code to simulate the performance of a heat exchanger. So our model calculates how heat is transferred and shows the different factors that affect efficiency. So some of the key concepts governing our code is the heat duty. The heat duty is the amount of heat that is transferred between the fluids. It depends on how much fluid is flowing and the temperature difference. We calculate the temperature using the log mean temperature difference. It represents the effective temperature difference between the hot and the cold fluids across the exchanger. This is because we can't just calculate for the average and assume it to be the temperature of the fluid. This is because in the heat exchanger, the temperature across different parts in the exchanger, it increases exponentially. And so the formula for the log mean temperature difference will be able to account for the exponential increase in temperature. We have the correction factor. So the correction factor accounts for the fact that real heat exchangers do not operate under ideal conditions. It adjusts the log mean temperature difference to reflect the actual flow arrangement, that's the fluid, ensuring that heat transfer calculations are accurate. We also have the effectiveness. So effectiveness shows how efficiently heat exchanger is performing as compared to its maximum possible performance. So when we run our code, we'll be given a prompt. This the code we ran on earlier. So we'll be given a prompt. So in the prompt, it asks if we want to run another code. And then Y is for yes, so we say yes, then press enter. So we see we're supposed to input or enter the fluid I want to use. Fluid can be liquid or gases. So liquid, we have water, air, or ethanol. And gases, you have air, then liquids, you have water, oil, or ethanol. So apart from our Python code that we developed, apart from these 4 types of fluid, it can calculate for other types. But then there are research. These 4 types of fluids are mostly used, is what's mostly used in various industries. So that's why we choose them. So let's assume our fluid here to be water. So let's take water and press enter. We are supposed to input our hot inlet temperature. So since it's high, we choose 120. We just assume it to be 120 degrees Celsius. The hot fluid at the outlet, since the heat exchanger removes heat from the hot fluid to the cold one, the hot fluid at the outlet will be lesser than the one in the inlet. So let's say it will be 80. Then the cold inlet temperature, let's assume it to be 30. Then that of the cold temperature outlet will increase. So let's say it increased by 4, so 70, by 40, sorry, so 70. we're supposed to input our flow rate. So let's assume our flow rate is 2.5. And let's also use 500 for the heat transfer coefficient. So our flow type, we can choose either parallel or counter. I will use parallel since we want to see the relation between the hot fluid and that of the cold one. So, okay, so it has run. So when we run our code based on the inputs that we gave, okay, so this is it. So this is our results that we got. So we had our heat density to be 418 kilowatts. So when we look through, this is the results that we got. Our effectiveness around 0.67. Our optimal area is 5.0 meters squared. So for the interpretation of our first graph, this is it. So our graph shows how the hot fluid cools down while the cold one heats up along the length of the heat exchanger. So we can see our hot temperature cool down from 120 degrees Celsius to that of an 80 degrees Celsius. And you can see the temperature of our cold fluid increase from 30 to 70 degrees Celsius. Okay, so this is a graph of temperature against length. Then we come to our graph of effectiveness against area. From our results, we saw that our effectiveness was 0.67, and then our optimal area was around 5 meters squared. But here, since we chose our flow type to be parallel, the blue line here only indicates that the 0.67 is the effectiveness at 5 meters squared area. Our graph is supposed to show an increase in effectiveness as the area increases. So a counter graph will show the increase in effectiveness as the area increases. Yes, so if let's say our area was 25, we see it will increase. Our effectiveness will be around 0.68. It will be more than that of the 5 meters squared area. So you come to our graph of cost against area. So this graph shows the cost increases as the area increases due to higher material and installation cost. Yes, so when our area increases, so a large surface area means that your heat exchanger becomes larger or bigger. Yes, and the more bulky it is, that's the more quality materials are used. That also increases your cost that also increases the cost of the heat exchanger too as well. So when we come to the next graph, you can see it's a graph of the U, that's the heat transfer coefficient against the time. So you can see effect of fouling. So one might ask, what's fouling? Fouling is the buildup of unwanted materials on the surface of the heat exchanger. It reduces transfer of efficiency over a period of time. So you can see that at time t is equal to 0. You can see that our heat transfer coefficient was 500. It was maximum. That was because there was no buildup in the heat exchanger. But as time goes on, the process gradually leaves deficits. So that makes the build up. And the build up, it doesn't just occur instantly, it occurs over a period of time. So this time might be in months or years. Yes, so you can see that at year 1, at t is equal to 1, you can see the heat transfer coefficient, it decreases from 500 to 450. Yes. So in our next graph, it shows the 3D efficiency surface of the heat exchanger. So you can see the effectiveness on this side. You can see the flow rate here and then the area here. So in our daily life, heat exchangers are used in systems such as air conditioners, refrigerators, and car radiators. In industry, they are used to recover heat, reduce energy waste, and improve overall efficiency of processes. In conclusion, this project shows how heat exchangers performance can be analyzed using computational tools. It also highlights the importance of heat exchangers in improving energy efficiency, sustainability in both industrial and everyday life. So this brings us to the end of our heat exchanger stimulation. So let us know the next load you want us to stimulate in the comment section. Thank you for watching.